Good afternoon, everybody. My name is Szymoszek from Knell, Germany, and I would like to present you a case study, QSAR calculation of octanol water partition coefficient logKow. The talk will be divided into 4 major parts. First, an introduction, then a practical part running selected models and analysis of results, followed by documentation of QSAR results in Euclid for each dossier preparation, and finally summary and conclusions. The goal of the case study is prediction of octanol water partition coefficient logKow using VEGA QSAR models and documentation in Euclid. And the target molecule is 2,3,4-trichlorobiphenyl, which is common for our case studies presented 2 weeks ago and today, where different models are presented. Models which are presented during this talk are VEGA, logKow or logP models, Malan-Kov-Wien, M-logP, and A-logP. For all of them, QSAR model reporting formats, QMRFs, are available. What we need as input data is just Smiles code of the molecule. So we may see it in the bottom. Okay, so very important for our series of talks is rich concept gateway. We have here the link, and we may find models which are applicable for partition coefficient and octanol water. So we have 4 platforms, and yes, so they include MBIT, VEGA, Danish QSAR database, and OChem. And for the purpose of this talk, we have selected 3 models which are available at VEGA platform. All are models which can calculate octanol water partition coefficient. And we have also other models, for instance, distribution coefficient, Danish QSAR database, or OChem models. So this is just restricted selection for the purpose of this presentation. And those VEGA models for octanol water partition coefficient are the following. Malan-Kov-Wien, it's actually a VEGA implementation of EpiSuite-Kov-Wien you are probably familiar with. And also M-logP and A-logP. And they have something in common. They are multiple regression models. But it should be pointed out very clearly that they are independent from one another. So using all 3 of them, we can get a more comprehensive picture of the situation of this endpoint for this molecule than in just one case when we have one model. Okay, now how to run models which are available at VEGA platform. Here we see the interface of VEGA. VEGA means virtual models for evaluating the properties of chemicals within a global architecture. It's developed mainly in Milan at Mario Negri Institute, and also a company called Code is involved from Pisa, so everything based in Italy. It's a free platform developed based on contributions from European Union projects. And for now, we have more than 100 statistical and knowledge-based QSAR models for the prediction of toxicity, ecotoxicity, environmental fate, and physicochemical properties of chemicals. Yes, so what we have to do is to enter our molecule, to paste the SMILES code. And then if we click on the plus, it appears in the list. Of course, we may have more than one molecules in our list, but for the purpose of this presentation, we have just one, which is visualized in the right panel. Then we select the models, so we have different possibilities. We select, as said, all three available octanol water partition coefficient models. We may also select water solubility or vapor pressure, or if we scroll down, we have also other physicochemical models. But for this presentation, we select 3 logP models. Okay, then we just select the type of report we want to get. Normally, it is a report in a PDF format where we have prediction results, applicability domain evaluation. We can also have information about experimental data, if available for the target, evaluation based on most similar substances, and other available info. So we may select such a single PDF report ordered by model or by molecule. This is really not relevant for our case where we have just one molecule. And we can also obtain simplified text reports, which are useful for Excel import, and so the results can be then processed in Excel. Finally, yes, so we choose the destination folder, and finally we click on predict, and really in seconds we obtain a report with predictions. So this is a screenshot from the report. So what we may here notice is this dot, which is yellow. That characterizes the outcome, the result, and if the logKow is low, from between 0 or actually can be also below 0, so it is below 3, then we have it green. And if the substance is highly hydrophobic, starting from 8 and greater than 8, we have it red. So in this intermediate region here between 5 and 6, we have it yellow. And we also may see that experimental value for our molecule is available. It is likely that for our predictions, which we will be undergoing in the future, this will not be available, this experimental value. But as said, this is just the substance which is common for all presentation in the series, and it is so selected that we may learn something from this case. We see the model prediction, and it is pretty close to the experimental value. And a very important sentence, that the predicted compound is into the applicability domain of the model. This is a result of consideration performed automatically. First of all, this is a calculation of the global applicability domain index. We have that this applicability domain index is 1. And also the similarity index. Well, I will not get into details about all those indices. I'm just saying that this global AD index is the most important, and it is obtained based on all other indices. And we just see that the similarity index is also 1, so they all take values between 0 and 1. And for the two first indices, it is good if it is as high as possible, so close to 1 or even 1. And 3 further indices, accuracy of prediction, concordance for similar molecules, and maximum error of prediction, this is the opposite. So actually they should be as low as possible. It will not also be the case that they take the same value, like here, 0.17. But this means that this value is pretty low, close to 0. So then if we take all into account, we get this applicability domain index of 1. So this is why we have this predicted compound into the applicability domain of the model. We have also similar compounds with predicted and experimental values, and we may also see that the differences between experimental and predicted values are low, meaning that the predictions are good because this is the good reliability. The difference is between 0 and 0.5 for logarithmic partition coefficient. Okay, then we move to M-log-P model. So now the difference is slightly greater between the absolute difference between the experimental value and model prediction, but it's still a good reliability. And the predicted component is into the applicability domain of the model. We only see that here those indices have now slightly greater values, meaning that perhaps it is not as good as in the previous case, but still very acceptable, and we still may speak about the compliance of the compound with the applicability domain of the model. And we now go to A-log-P, and here we have something different. The predicted compound could be out of the applicability domain of the model. Could be out. That means it's a kind of gray zone, because we may also get a message that it is definitely out of the applicability domain. So in this case, it is just, it could be out, and it is marked in the color code as this yellow triangle, because the global applicability domain index is not 1 anymore. It is just 0.85. And yeah, so one may think, well, it's still high, but it only means it can be interpreted for this model that the predicted compound could be out of the applicability domain. Well, the similarity index is still 1, but the accuracy of prediction for similar molecules, the concordance and the maximum error are now not that low. They are slightly higher than 0.5. Meaning that those indices are not so good as previously, and we have this global AD index not of 1 but only 0.85. We may also see slightly greater differences for similar compounds. So we may summarize the results in this table, where we have 2 times into the applicability domain, and for this model could be out. The deviation here is greater than 0.5, so it is not good anymore. It is just moderate, and we see that for 6 similar molecules, for those 2 models, we have 6 times good performance, and in this case of A-log-P, this is 4 times good and twice moderate only. So we get conclusion, which we actually expect, that the better the compliance with the model applicability domain, the more precise the result. Some important remarks about VEGA. As said, full documentation of all models, of all three models, is available as a QMRF, and supporting information is provided. So this is relevant for the dossier preparation in Euclid. And this very important AD evaluation, applicability domain evaluation, is performed automatically. It is, of course, based on identified similar molecules from the training or validation set. In this case, we had only training set. And we just have to state that the automated applicability domain compliance check is not perfect, and it is helpful to perform also user expert critical check. And 2 weeks ago, it was presented a novel tool called VERA, developed aiming at improving similarity evaluation and AD compliance check. And it was presented, so this is just to remind you, this very interesting presentation. And of course, this expert critical check is also, this is not restricted to VEGA models. This affects other tools as well, including commercial ones, that everything that is automatic can be supported by expert critical check. Okay, now to the Euclid part. So right from the start, we have to select of course, the endpoint, the type of information, which is QSAR. This is all based according to ECA Practical Guide, How to Use and Report QSARs from 2016. So adequacy of study, normally it is weight of evidence or supporting study. In some situations, it could be also a key study. Reliability is important. According to ECA Practical Guide, it should normally be a maximum of 2, so not 1, which is actually restricted for very, very decent experimental studies under GLP. But it can be said that actually it should also be a minimum of 2, because then we have, with restrictions, but still a reliable result. And it should be selected based on what we get in the VEGA outcome and our expert assessment. So here it's quite straightforward, because we have the following rationale for reliability: results derived from a valid QSAR model and falling into its applicability domain with adequate documentation and justification. Then a very important field in Euclid, justification for type of information, and we have 6 points which are relevant for QSAR. And 3 first of them are pretty straightforward. We just have to write down the software, the model, and the smiles. And then 3 further ones are more sophisticated. But if we have a QMRF, for instance, for this scientific validity of the QSAR model, we may just provide a reference to our QMRF, which in the next slide will be shown where it can be attached. Applicability domain, we can also attach our VEGA report and also reference it here, but we may also add some information if we perform an expert assessment, which is also the case of the adequacy of the result for the regulatory purpose, where we need to also state a couple of words how the prediction fits the purpose of classification and labeling and the risk assessment. So this is then relevant for adequacy of the result for the regulatory purpose of REACH. So in the next section, we just attach this QSAR model reporting format. And also we may attach our our report with results as a QSAR supporting information. If we have a PRF, it can also be attached. It is not provided by VEGA in output, so we have only this result report. But of course, if it is available, it can and should also be attached here. Yes, then data source, information about the software and model, materials and methods. We should provide this ECA guidance R6 on QSARs. Otherwise, we may also use the test guidelines used to generate the data for the training set. And principles of method, if other than guideline, we may provide information about literature references. So this is all about this Malan and Kofwin model. Then QSAR results. Yeah, so we have test material information, SMILES code, and the test material must correspond to the structure. And in some cases, if you have multiple constituents, if you have a multi-constituent substance or a UVCB, then it is suggested that for each representative constituent, we prepare separate Euclid entries. Here, of course, we have just one structure, so it is enough to have one Euclid entry. And so this is the result, and we also should provide a remark that information on, because it is not experimental results, so we have no information on temperature and pH as a remark. Okay, to summarize, here again, this link to our gateway, concept-rich gateway, which is available for your QSAR predictions for reach and other purposes. What was presented was QSAR prediction using 3 VEGA models and evaluated, and also preparation of a QSAR Euclid entry for logKow, one entry of Malan-Kofwin model was presented, and we focused on critical fields which are important, especially for QSAR results. The conclusion is that applicability domain compliance is the most important factor that should be taken into account when evaluating the reliability of QSAR results. So we saw for 3 models we have accepted without special restrictions just 2. And those predictions may be used in the context of reach, either to cover the endpoint fully if we don't have any other information, or together with other information, preferably experimental data as supporting data or part of weight of evidence. Thanks to all involved colleagues, the CNOL Academy team, the team at Mario Negri Institute led by Professor Benfenati, the QSAR team at CNOL, the speakers of today and 2 weeks ago, and all partners of the Live Concert Reach project. Logos are available here. Thank you, and if you have questions, please move ahead. Thank you very much.